Light. Light plays an important role in our life. It produces the sensation of sight and makes the things visible to us. The sun is a natural source of light. We cannot see an object in the dark. It means that eyes alone cannot see any object. It is only when light from the object enters our eyes we can see objects. The light may have been emitted by the object or may have been reflected by the object. The rest get absorbed. The bodies which emit light are called luminous bodies. The sun, stars, burning candle, filament of an electric bulb are luminous bodies. Luminous bodies may be natural or man-made. Sun, star and firefly are natural luminous bodies. A glowing electric lamp, a burning candle are man-made luminous bodies. The bodies which do not emit light are called non-luminous bodies. Examples: table, chairs, earth, moon, etc. Light travels in a straight line. Switch on a torch in a dark room. Can you see a circle of light in front of you? Move the torch to your right. You will now be able to see objects on your right but not in front of you. Why do you always see only the objects directly in front of the torch? This is because light travels in a straight line. Have you ever seen the light from the cinema projector traveling to the screen in front of it? Are there any other ways to find out whether light travels in a straight line?
Activity 1. Take 3 cardboards of equal size.
Make a very small hole through the center of each. Make them stand on a table with the help of some support like modeling clay. Place the cardboards in such a way that their holes are in a straight line. Light a candle at one side of the table in such a way that the flame is in line with the holes. Look at the flame from the other end through the holes. Are you able to see the flame? Why? Now, move the middle cardboard slightly so that the holes are not in a straight line. Can you still see the flame of the candle? No. Thus we conclude that light travels in a straight line. The property of light traveling in a straight line is called rectilinear propagation of light. Reflection of light. What does an object do to the light that falls on it? It may allow the light to pass through as a glass sheet does. Figure A. Or it may completely cut off the light by absorbing the light, as in the case of opaque objects like wood. Figure B. A third type of surface, like a polished mirror, bounces back the light into the medium from where it comes. Figure C. When light falls on a surface, light bounces off the surface. This bouncing back of light from a surface is called reflection of light. Regular and diffused reflection. When light falls on a smooth or polished surface, the surface reflects the light in a well-defined manner. This is called regular reflection. Regular reflection takes place on a mirror. On the other hand, when light falls on a rough or uneven surface, it gets reflected and scattered in all directions. This is called diffused or irregular reflection. Diffused reflection does not give rise to image formation. Diffused reflection can take place on a wall, a wooden almirah, or other surfaces. Activity 2. Aim to show that smooth and polished surface produces image when light falls on it. Materials required: polished top of a table, near the wall, torchlight and dark room. Procedure: put off the lights at night and direct the torchlight at an angle on the dining table which has a smooth and polished surface. Adjust its position so that light striking the table changes its direction and appears as spot of light on the wall at the other end of the room. Observation: when you move the torch to different locations on the table, The spot of light on the wall also moves. Conclusion. The image of the torchlight is formed after reflection from a polished surface if it is directed in a particular inclination. Laws of reflection. There are two laws of reflection mentioned below. 1. The incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. 2. The angle of incidence, angle I, is equal to the angle of reflection, angle R. That is, angle I is equal to angle R. During the day, we see light all around us. This perception comes as we are able to see things around us. Image formed by a plane mirror.
Activity 3.
Aim. A. To observe image formed by a lighted candle from a plane mirror.
B. To read few alphabet from its images in the mirror.
Materials required: plane mirror mounted on a stand, drawing board, sheet of paper or brown paper, a lighted candle, and paper with alphabet written. Procedure. A. Draw a straight line on a sheet of paper. Place a plane mirror mm- on the line. Vertically erect. Cut a brown paper in the shape of equilateral triangle. Place the brown paper with one base of the equilateral triangle touching the mirror. Place a lighted candle along the side of the triangular brown paper. Move the candle along the side of triangular paper closer and farther from the mirror mm-. Also, shift it from right to left side of the triangle. Here, the candle serves as an object and the mirror mm- represents the reflecting surface. B. Try to read few alphabet by facing the paper to the plane mirror. Observation and conclusion. A. The image of the candle is upright, the flame pointing upwards, and is of the same size. B. The image behind the mirror is at the same distance as the candle is in front of the mirror. When the candle moves away from the mirror towards the tip of the triangle, the image also moves in the mirror to the same distance on the image on tip of the triangular paper. C. The image formed is laterally inverted, that is, left side appears as right and vice versa. D. The image formed is always virtual. If screen is placed in front and then behind the mirror, there is no image of the candle or the triangular paper obtained on the screen.
E. The letters P, D, B are inverted laterally while A and X are not. Activity 4.
Aim. To show that plane mirror produces lateral inversion. Materials required: a plane mirror, a white sheet of paper. Procedure. Write your name on a sheet of paper and hold it in front of a mirror. Observation. You will see that your name has been completely reversed. Now take white sheet of paper and over it write a letter P. Place it in front of the mirror. The letter P will appear as shown in the figure. Characteristics of the image formed by a plane mirror. 1. Image is virtual. It means the image cannot be taken on a screen. 2. Image is of the same size as that of the object. 3. Image is formed as far behind the mirror as the object is in front of it. 4. Image is laterally inverted. It means left hand side of the object appears as right hand side of the image and vice versa. 5. Image is erect. Multiple images formed by two mirrors inclined at an angle. When two mirrors are placed inclined to each other at an angle, many images of the object placed before them are seen. This is because the image formed in one mirror acts as the object for the other. The number of images seen, however, depends upon the angle at which the two mirrors are placed. When the two mirrors are placed parallel to each other, a large number of images are seen. When the mirrors are placed at right angle to each other, 3 images of the object are seen. These two cases can be described more clearly as when the two plane mirrors are placed at right angles to each other and an object is placed in front of the two plane mirrors, 3 images are formed as shown in the figure given. The image I1 of the object O is due to mirror 1. The image I2 of the object O is due to mirror 2. The third image I3 may be considered to be the image of I1 in the image of the mirror 2 or the image of I2 in the image of the mirror 1. Thus, the image I3 is an overlap of two images. Thus, the image I3 is brighter than I1 or I2. When the two plane mirrors are placed parallel to each other, let us consider an object O placed in between the two plane mirrors held parallel to each other. The image of the object in mirror M2 is formed at I1 as far behind the mirror as the object in front of it. The image I1 acts as object for mirror M1 and its image is formed at I2. The image I2 then acts as the object for mirror M2 and the corresponding image is formed at I3. This process of image formation continues and an infinite number of images are formed in the mirrors. In actual practice, however, only the first few images are sharp and can be seen clearly.
Activity 5.
Aim: to see images formed using two mirrors. First, let us see what kind of images we would get by using two plane mirrors and candles placed at different angles. You know, by varying the angle between two mirrors, we can get any number of images. You might have noticed this in many places. Some shops have mirrored walls. If you try to look at yourself, you will see that there are an infinite number of images. Also, you might have noticed this in some temples, where you see an infinite number of images of God statues in the mirrored walls. Now, try to look at your back in a mirror. You would not be able to see your back in one mirror. You need two mirrors. Whenever you get your hair cut at the barber's shop, barber always holds a second mirror behind you to show your hairstyle in the mirror placed in front of you. All these are the cases of multiple reflections of light. Uses of plane mirror. We use plane mirror in our homes as looking glass. It is used in optical instruments like kaleidoscope and periscope. It is used in solar cookers. It is used to maintain distance chart for testing eyesight. Refraction of light. You have learned that light travels in a straight line at a uniform speed and the plane, spherical or polished surface reflects light in a regular way. But when there is a change in the medium, as for example, light falling from air to surface of water or from air to a piece of glass, strange visual effects are produced, bringing about changes in speed and direction of light. Very little of the light incident on the surface of clear glass or water is reflected back. When light travels from one medium to another, it changes its path, that is, bends. This bending of light is called refraction of light. Activity 6. Aim: to observe the change in speed and change in direction of light when light enters from one medium to another medium. Materials required: glass, water, milk, dark room, and torch. Procedure: fill a glass with water, add a little milk to make it cloudy. In a darkened room, switch on the torch. Shine the beam of light from the top to bottom at an angle of 45 degrees on the surface of water. Observation: you will notice some light entering the water with its path slightly bent from its straight line path. Now, fill the glass with clean water. Put a stick in the glass at an angle of 45 degrees. The stick seems to be broken and bent at the point where it enters the water. Conclusion: when light passes from air to water, and usually from one transparent medium to another, it changes its speed, which in turn causes a change in direction. We call this refraction. This can make an object appear to be in different position to where it really is. Understanding refraction. Refraction can be explained in terms of change in the speed of light and its direction when it passes from one transparent medium to another. A. When a ray of light passes from a less dense medium, air, into a more optically denser medium, water, it bends towards the normal as its speed decreases. B. Conversely, when a ray of light passes from a denser medium, water, to a less dense medium, air, it bends away from the normal as its speed increases. Refraction through a glass slab. When light travels from air to glass, it bends towards the normal as air is rarer medium and glass is denser. When it emerges from glass to air, it bends away from the normal. Emergent ray is parallel to the incident ray. The distance between the emergent ray and the incident ray produced is called lateral displacement. Refraction through a prism. A prism is a solid triangular glass block. The figure shows the path of light when it passes through a prism. Here, a ray PQ incidents on the surface of AB of the prism ABC and bends towards the normal. Refracted ray QR, when emerges from the face AC of the prism, it bends away from the normal. Here RS is emergent ray. Dispersion of white light. Sir Isaac Newton was first to obtain the spectrum of sunlight by passing the sunlight through a prism. Experiment. Newton passed narrow beam of sunlight through the prism. The light emerging from the prism was allowed to fall on the white screen. The light received was in band of 7 colors. The order of colors is violet, indigo, blue, green, yellow, orange and red. Violet color bends most and the red color bends least. This band of distinct colors is seen as a beautiful rainbow. You must have noticed that whenever oil spills on the water, it forms an oil film on the water and shows different colors. This occurs due to the dispersion of light. Both the top and bottom layers of the oil film reflect white light through the oil film and water. As a result, we see colors of thin oil film on water.
Activity 7.
Aim: to view the spectrum using a prism. Materials required: a plane mirror, transparent containers, sheet of white paper. Procedure: take a long plane mirror, place it on a container, transparent, without design's glass container or tumbler. Dip or place the mirror at an angle of 45 degrees in the container filled about 3/4 with water. Place this container along with the mirror facing the sun near a window. Adjust the direction of the mirror by moving the container so that the reflected sunlight falls on the wall. If the wall is colored, fix a sheet of white paper on it. You will see a beautiful colorful spectrum like an inverted rainbow on the wall. Get a sharp spectrum by shifting the container. The container becomes a prism by a combination of water and mirror. How does this happen? Lenses. Apart from curved mirrors, lenses also can change the quality of image. You have seen your father or your grandfather using a piece of glass to read some fine print in the newspaper. He uses a magnifying glass, which is actually a lens. If you observe, you will notice that lens is a piece of transparent glass which has polished curved surfaces. A lens can be concave or convex in one or both the faces. The convex lens bulges in the middle, the concave lens bulges at the ends. Terms related to lenses. Principal axis. The line joining the centers of two spheres from which the lens is formed is called principal axis. Optical center. The center of the lens is called optical center. It is denoted by O. Principal focus. The point on the principal axis where parallel beams of light rays meet or appear to meet is called principal focus. It is denoted by F. In convex lens, all the parallel beams of rays of light meet, converge at one point focus after passing through the lens. Therefore, it is called a converging lens. On the other hand, in a concave lens, beams of light rays parallel to principal axis spread out away from the principal axis and appear to be coming from a point. Hence, it is called a diverging lens. Focal length. The distance between optical center O and principal focus F is called focal length F. Images formed by spherical lenses. A. Convex lens. The magnifying glass is a convex lens which magnifies the image if held close to the object and the image is upright. As the lens is moved away from the object, the size changes from large to small and the image becomes inverted. The image from a convex lens, when erect, will be virtual, and when inverted, it becomes real. That is, it can be projected on a screen. The nature of the image for different positions of object in a convex lens is given in the following table. Position of object, position of image, nature of image. Between principal focus F and optical center O, on the same side as object. Virtual, enlarged, magnified, erect. Between F and 2F, beyond 2F on the other side of lens. Enlarged, real, inverted. Beyond 2F, between F and 2F on the other side of lens. Real, inverted, smaller in size. B. Concave lens. The image from a concave lens is always upright and smaller than the object, and it cannot be projected on a screen. That means the image is virtual. I. The natural optical instrument.
The eye is the sense organ which helps us to see clearly. It helps us to identify shapes and colors of objects around us. The human eye is spherical in shape. Structure of the eye. The different parts of the eyes are: A. Cornea, the outermost transparent layer at the front of the eye. It helps in focusing of light into the eye. B. Pupil. It is just behind the cornea. It is the hole in the center of iris. It allows light to enter through it. C. Iris. Iris are muscles that regulate the amount of light entering the eye. Iris are the colored part of the eye. In bright light, it expands to reduce the size of pupil. In dim light, iris contracts to increase the size of pupil and to allow more light to enter the eye. D. Lens. It is a jelly-like structure placed behind the iris. It is transparent converging lens. It helps focusing light on the retina. E. Ciliary muscles. These muscles keep the lens in position. They control the lens's focal length by changing the lens thickness. F. Retina. The area where light rays fall. It contains light sensitive cells, cones, and rods. Rods are not color sensitive, while cones are color sensitive. G. Optic nerve. It carries impulses from the retina to the brain. The region between the cornea and lens is filled with transparent liquid called aqueous humor. The region between lens and retina is filled with jelly-like transparent substance called vitreous humor. At the region where the optic nerve meets the retina is the blind spot. Here, in this area, there are no light sensitive cells. So, image of any object falling in this spot cannot be seen. Functioning of the eye. The amount of light entering the eye is controlled by the iris muscles, which increases and reduces the pupil depending on the brightness of light. When light from far away objects falls on the lens, it becomes thinner due to the action of ciliary muscles. The focal length changes to maximum as the ciliary muscles relax. When objects come closer, the ciliary muscles make the lens thicker, thus reducing the focal length. The lens and ciliary muscles have the ability to focus the image of the object on the retina at a distance of 25 cm. This is the smallest distance for a clear image to form on retina. The lens's focal length cannot be reduced any further. If the object is brought closer than 25 cm, then image becomes hazy. Images formed on the retina is sent to the brain by the optic nerve. Thus, the images formed can be seen by us. The ability of the lens to alter its focal length according to object's distance in order to see clearly is called accommodation of the eye.
Defects of vision. Certain people have difficulty in seeing things. The abnormalities in the normal vision of the eye are called defects of vision. The most commonly observed defects of vision are A. Myopia, short-sightedness, B. Hypermetropia, long-sightedness. Myopia, short-sightedness. A person suffering from myopia or short-sightedness can see the nearby objects clearly but cannot see the far-off objects clearly. Thus, short-sightedness, myopia, is a defect due to which a person is not able to see the distant objects clearly, though he or she can see the nearby objects clearly. Causes: myopia is caused by following reasons. A. Decrease of the focal length of the eye lens. B. Elongation of the eyeball, that is, increase in the length of the eyeball. Correction of myopia.
The myopia, short-sightedness, can be corrected by making the eye lens less convergent.
So, myopia, short-sightedness, can be corrected by using a concave lens of suitable focal length. This is shown in the figure. Hypermetropia, long-sightedness. A person suffering from hypermetropia, long-sightedness, can see the distant objects clearly, but cannot see the nearby objects clearly. The long-sighted persons have difficulty in reading. Causes: hypermetropia, long-sightedness, is caused by the following reasons. A. Increase of the focal length of the eye lens. B. Shortening of the eyeball, that is, decrease in the length of the eyeball. Correction of hypermetropia. Hypermetropia, long-sightedness, can be corrected by making the eye lens more convergent. This is done by placing a convex lens of suitable focal length before the eye lens. So, hypermetropia or long-sightedness can be corrected by using a convex lens of suitable focal length. This is shown in the figure alongside. Persistence of vision. When we see an object and its image is formed in front of our eye, the image of such object persists at our retina for some time, that is 1/16 of a second. This is called persistence of vision. This property is used in cinematography. Role of nutrition in relation to blindness. In a healthy body, minimum daily requirement of vitamin A is 600 microgram. The deficiency of vitamin A can lead to poor vision or night blindness. Vitamin A is present in large quantity in milk, cheese, tomatoes, carrots, cod liver oil, cabbage, mango, spinach. Deficiency of vitamin A leads to night blindness. A person suffering from night blindness can see during the day but cannot see at night or in dim light. Care of eyes. The sense of sight is the most important. The following are simple ways to protect our eyes. 1. Be careful for your eyes while playing or doing any work. 2. Wash your eyes with cold water 3 or 4 times in a day. 3. While reading or watching television, blink your eyes from time to time. 4. You should not read in a moving bus or train. Also, in dim or bright light, you need to be careful so that your eyes don't hurt. 5. When in case dirt or insect gets into your eyes, you should not rub them. It can harm the eyes. Wash your eyes with clean water or consult the doctor.